Okay. All right. So how are you guys? So did you see I made an announcement today online, moved a couple of deadline dates around, tried to alleviate some pressure with deadline dates. So I think it makes it a little easier for folks. The take-home isn't due until the end of finals week. So you'll finish the in-class first, then the take-home. You can always turn in the take-home early if you want to just get it done. That's fine. But it'll be due the Friday of finals week. Move the paper down, final draft of the paper down by a few days. That'll allow me to get feedback to you without having it being due next Wednesday. So you'll have a few extra days for that. Yeah.
If we wanted to start, is there like going to be a way explanation on how to do the last section?
There was a posting on that. I mean, if you check the assignment,
Okay.
So that was published, so that's up. So you might want to take a look at that.
Okay.
Basically, though, really all you're doing in the discussion is, there's a few things you want to cover. One is strengths and weaknesses of the research. Like, given that you've designed this research project, as you look back on it, what do you think the strengths are? What are the weaknesses? Are there any potential confounds? Things that you might do differently so that if you had to, say, do a follow-up experiment, what would you do? Okay. So I would look at that. And so that leads to the next thing, which is, okay, how does this become the start of a research program? In other words, what would be the subsequent studies that would come next? So and you might want to talk a little bit about how your findings would contribute overall to this particular research field. But the discussion is not meant to be especially long, maybe a few pages at most. Just provide some perspective on it. The bulk of this paper really is the intro and the method, right? Because that's what this class is, right? It's sort of, learning how to do lit reviews, learning how to design studies. And then, and in that method, you need to be able to describe the analyses that you'll run and what you expect to find, okay? So, really, I think the bulk of the work for you at this point is probably done. What I'd really encourage you to do is to continue to revise the intro, continue to refine your methods, okay, because that's where most of the points are going to be, okay? And the discussion should be, good and concise and on target, but shouldn't represent the focal effort for this paper, okay? Okay, so, it's an exciting day. It's correlation day. How about that? Everybody's just ready to go. We've been waiting all semester for correlation. And here it is, finally. Okay, I actually really enjoy going over correlation, regression. Got some interesting stuff, especially when we hit regression. So, and we'll start today by showing how they're related to one another. Okay, so up to this point, our main focus has been on looking for differences in means, right? In some way. In a t-test, we were testing for differences in the means. In ANOVA, we were comparing between treatment variance to within treatment variance. The only way to get between treatment variance is by having variation in those means. Okay. But what if our question doesn't involve mean differences? What if we're interested in associations and the degree of relationship between two variables and interested in quantifying that relationship? Now, it's certainly the case that t-tests and ANOVA speak to relationships between variables, right? If you have a statistically significant t-test, what you're saying is that there is, in fact, a relationship between the independent variable, which is usually categorical, and the dependent variable, which is what you're measuring, right? And you're saying, the treatment group performed better on some dependent measure than the control group. I got a significant t-ratio with a significant p-value, right? So that does show a relationship. So it wouldn't be particularly accurate to say that when we look at t statistics, t ratios and Fs and ANOVA and everything, that we're not looking at relationships. We absolutely are. And in fact, correlation, regression, t-tests, ANOVAs, They're all part of the same statistical model. Okay, so there's an underlying model called the general linear model. Okay, in fact, SPSS is set up that way, right? You see menu choices that reflect the general linear model. And the general linear model is essentially an additive model. It basically says that variables may explain variance in other variables in an additive fashion. Okay? And we don't spend a lot of time on that underlying mathematical model, but it's shared between ANOVA, t-test, regression, correlation. Okay, it's all the sort of notion of additivity. Okay, now, but the focus clearly with ANOVA t-test is looking at mean differences and seeing if means are different, especially amongst categorical variables, but it's not always the case that we have just categorical variables. Maybe we don't want to classify our subjects in terms of categories. Maybe we just want to score them on a measure and look to see then what the relationship is on scores on one measure to scores on another. So what is a correlation? Helps us understand the degree of association between two variables, and there's two parts to it. The magnitude, which is the absolute value, and the direction, which is the sign. So correlations can range from what to what? From, say it again? Negative 1 to 1. And the 0 would be what?
No correlation.
No correlation, right. So 0 means no correlation. Positive 1 means a positive relationship. So that as the scores on X increase, so do the scores on Y. Conversely, as the scores on X decrease, so do the scores on Y. So they're in synchrony. Negative relationship is also called an inverse relationship. So as the scores on X go up, the scores on Y go down. Okay? Okay, as the scores on X go up, scores on Y go down. So, example of a positive relationship might be number of drinks that you have at a party and your performance on a reaction time task. Right? As number of drinks go up, your reaction time increases.
Length of the reaction.
Yeah, length of reaction time increases. Okay? So, except if you ever saw an old show, WKRP in Cincinnati, Johnny Dangerous, they tried the test on him. The more he drank, the faster his reaction time got. Totally blew away the researcher who was trying to work with him.
That's not average, though.
What?
Any one individual might be at the extreme.
Yeah, and it's not
average.
And it's not necessarily linear. In other words, there's some research to show that when you initially start drinking, your reaction time actually gets better. It's then after the first couple of drinks.
Yeah,
Start having
maybe
problems.
one reaction, one might inhibit some of your thoughtfulness.
Right.
You might react quicker, but then after 10,
But after that,
after
not so
10
much.
you're just almost full.
Yeah, but that's important to note because that's a nonlinear relationship at that point, right? Okay, so positive correlations, they can be weak, they can be strong, right? And no correlation effectively means that if we know something about X, we know the value of X, it tells us nothing about the value of Y, okay? So it's not helpful. Okay, so correlation is really the first fundamental building block of this process we're going to explore over the next couple of lectures. The second part to it is called regression. Okay? Now, regression gives us more information than simply the degree of association between two variables. What we can get out of a regression is actually an equation that's going to help us to predict how much change in a predictor variable we should expect for every unit change in a dependent or criterion variable. Actually, I think of those should be reversed. How much change in the dependent variable for every unit change in the predictor variable. Okay, so once we know the scores on the predictor variables, here's the main point. We can then predict scores on the dependent variable with some error. So what makes this different is that we're not looking just at the relationship between two variables and the strength of the relationship. What regression allows us to do is actually predict scores. Once we know a score on X, we can predict the score on Y. Okay? So what that's going to require us to do is to create what's called a regression line that fits our data and represents a prediction of what Y should be given what we know about X. That sounds pretty abstract right now, but you'll see in just a moment what that refers to. Imagine that we have a scatter plot of data, so these little diamond shapes represent the data. Okay? In a regression, we fit the best fitting line through that scatter plot. Okay? Now you might say, well, how do you know what the best fitting line is? Right? Because technically you could run an infinite number of lines through the data. Okay? But we're going to have just one line that fits the best. And I'll give you a little hint as to how we know which line to choose. For every data point, okay, that we run that line through, for every data point, we can compute the difference between the data point and the line. So again, remember, the line represents prediction. So if you have an actual data point that fell here, so over here we have our dependent measure scores, and over here we have scores on predictors on the x-axis. So y-axis is scores on the dependent measure, x-axis is scores on the predictor. So what this is saying is, given a score of 2 on our predictor variable, the prediction for y should be right here on the line. Okay? And how do we know that? We just draw right angles from the axes over to the line. The difference, which is this little red spot, right, the line going down the data point, is called error, okay, or residual error. Okay. So a regression equation is going to have certain components. It's going to tell us where the intercept is with the y-axis. It's going to tell us the slope of the line, okay? And then there's going to be an error term that represents how much error we have in prediction, in actually predicting the y value, our outcome variable. So we get this really sort of hairy looking equation, right? But all it's saying is the score on our dependent variable y is a function of the intercept, which is right here, and then for every predictor x, each of these predictors will have a weight. It's called a beta coefficient. Okay? And that beta coefficient weights the x value. That creates a regression equation. And then to get the actual value of y, the regression equation, by the way, results in this line. The actual value of y is then going to be this regression equation plus error, right? Notice how none of these data points fall right on the line. They're off the line a little bit. Okay, that represents error. So what this is saying is we have this regression equation. To find the actual value of y, we add error in, and then we figure that's what y is going to be. Does that make sense? Yeah.
So is beta the slope?
Beta is the slope.
So it changes every time?
Yeah, you'll have a different slope coefficient for each variable. So you can kind of think of that's the way the line tweaks to different angles. Okay? So these are the standardized beta coefficients, is what they're called, but you just call them the weights. Okay, so the good news for you in all of this is you don't have to do this by hand. We're going to let SPSS do a lot of the work. So again, I want you to think of SPSS as coming to your rescue, right? So we could do it all by hand, but it's a lot to do. We're not going to do that. So we're going to do SPSS. But I want you to understand how we get to this equation. This will come back to haunt us in the next lecture. Okay, so let's go back to correlations. Correlations are in fact tested for statistical significance. In other words, we're going to test whether or not a correlation, given our degrees of freedom, is large enough so that we consider it not to have occurred by chance or measurement error. Okay, there's a degree of association that's too big to have been likely to have been by chance. We express the null hypothesis as, anybody want to take a shot at what that symbol is?
P.
Yeah, you're going to want to say P. Everyone's going to want to say P.
Everybody say phi.
It's not phi. It's rho.
Rho.
RHO. Okay, so in the population, the null hypothesis would be in the population, the correlation between two variables is 0. Does that make sense? That the null should be that there is no relationship between two variables. At this point, that should seem really, second nature, right? And the alternative hypothesis is that rho is not 0. Okay, that there's some sort of relationship there that's likely not due to chance or measurement error. Okay, so rho is the statistic that we use when we're talking about correlations in the population. The statistics, so that would be the parameter. The statistic that we'd use if we're talking about correlations in a sample is R. So just R, lowercase r. Okay, so let's just walk through how this would work. So here's a scatter plot. And who wants to interpret that for me? What is that scatter plot telling you?
Positive correlation.
Positive correlation. You know that because of what?
As y is increasing, x is increasing.
Yeah, as y goes up, as x goes up, y goes up. Okay. So positive correlation. As it gets hotter, not surprisingly, more people go to the beach. And if we were to run a line of best fit through those data, it would go like this, right? Fit right through the cloud. And again, I'm not telling you yet how we get the best fit, but be thinking about that because it's going to involve error. Okay. So all the different patterns. This would be a perfect positive correlation. Okay. Why is it perfect? There's no error. Perfect. Excellent. Okay. The data points fall right on the line. This is a strong positive correlation, but it's not perfect. Right? Yeah, we'd like to see this.
Perfect. It's like
Well, if you have a perfect correlation, basically you have two variables measuring the same thing. Right? So you don't want to see perfect correlations because then you have a situation where the variables are completely redundant, not needed. You only need one. Okay? So here this is strong positive, and that would be weak positive. Notice that we get weaker relationships the farther those data points fall away from the line. You also notice that the line's beginning to what? As you get to weaker relationships. It's getting to flat. Yeah, it's flat. And so if you had a zero correlation, notice how it's hard to know where this line should go. Right? Probably flat is the best fit. So zero correlation is going to show up as a flat line when you chart the coordinates. And then the same thing goes for weak, strong, and perfect negative correlations. How you guys doing? Good? Okay, not so hard. Now, here's where we can run into some trouble with a correlation. It's not uncommon to have what we call curvilinear relationships. Okay? Curvilinear relationships are relationships that do not look like a straight line. So, for example, the problem with this is that correlation is a linear statistic. It's assuming, again, this is the additive model, it's assuming that as x increases, y increases to get a positive relationship. That's a positive linear relationship. Notice what's implied when I say as x increases, y increases. I'm essentially implying additivity to x and y, right? I'm not multiplying. I'm just saying as x goes up by 1 unit, y should go up by 1 unit for a perfect correlation. Okay? But what if you had something that looks like this? right? So this is the classic example that's given for a curvilinear relationship, and it's probably one that you might be able to relate to. Okay, what happens if, say, for example, people vary in terms of their anxiety going into a test? We also know that their scores will vary. And what if we found this kind of inverted U-shaped relationship? So down here, what's going on with these folks?
Don't care enough to do well.
Yeah, those are the folks who have low anxiety, probably don't study enough, right? Maybe, it's just not important to get a high grade. And maybe a value thing, who knows, right? But low levels of anxiety, right? So they're not motivated enough to study, and performance is low. Then you get to the moderate group, and what do you see in terms of performance?
Anxiety helps to motivate them to do better.
Right. Yeah, so here's the thing. When you're a student, it's no fun to be anxious. But anxiety serves a purpose. Just a little bit, right? Not like catastrophic anxiety.
Well, it's because, just like a little bit of anxiety is going to make sure you run away from that cheetah the day when our senses evolved.
It's exactly the same system.
But
Right.
too much anxiety and you were a deer in the headlights.
That's
and
right.
You fail your exam or get eaten by the cheetah.
Right. So when people get anxious, they typically do things to reduce their anxiety, right? So if you're anxious about a test, one of the ways you can begin to reduce your anxiety would be to what? Study, right? So anxiety is a motivator, right? When people are a little bit anxious, they want to do things to reduce their anxiety. Okay, so what this graph is telling us, hey, if you have moderate anxiety, that seems to be, we assume, motivating folks enough, and that's helping to explain the higher scores. But then you get out here. What's going on with this group? Way out on the right side of the horizontal axis. What's going on with that? This is, Shannon.
Their anxiety is so high that they struggle to remember material or something, and then because they're so anxious, they start second guessing themselves. So
Yeah, this is the paralysis group or the panic group, right? The folks who, they'll get so anxious, and this really does exist, by the way. This is not.
Anxiety. It's
Test anxiety.
thing.
Yeah, and usually these folks have anxieties about other things too. It's not just tests, but it manifests itself. Okay, Rihanna, I know you need to talk about it. Go for it. Tell us.
I'm just saying, hello, yes, I am
Yes,
this person.
you're that person. So what happens is they get really anxious, right? And then they start freezing, right? Blanking out. And what's interesting is the fear response, the fight response, okay, is characterized by folks feeling really anxious or scared to begin with. And then some folks will run, but others will just freeze, right? And what you'll hear a lot in these folks is they'll feel like, they'll say things like, I was so nervous I blanked on the test, or I just couldn't focus, and their anxiety overcomes them, so their scores go down. So you get this inverted U relationship. Now, here's an interesting question. What does that line look like if I put it through the data cloud, right? I can put it right through that scatter plot. The best fitting line actually is going to be a straight line, okay? Because in a general linear model, I can't bend that line, okay? Can't do it. So I've got to keep the line straight, and the line that minimizes error, and I'm going to come back and talk more about that, but the line that minimizes error is going to be a flat line, okay? And a flat line suggests to us what?
No relationship.
No relationship. But are we, in fact, with our eyes observing a relationship? Yeah. So we know there's a relationship there, but the correlation will tell us that there's not a relationship. Does that make sense? Yeah.
So how would you detect a current relationship if the data would probably show you that there was no relationship?
Yeah. So what you do is you analyze residuals. Okay. So basically what SPSS will do is it'll create a plot, and then it plots the residual error for every data point. As long as the residual error seems to be about the same across the entire regression line, that doesn't look like there's any pattern to it, you're okay. if there is a pattern, what you could get, is what looks either like a spiral effect, okay, or some sort of curvature in the residuals. So that's a really good question. There are ways to diagnose this. So basically, if I were to just flatten the regression line, whatever it is, just so that it was flat, and then plot the residuals against that regression line, not the actual data points, but the residual amounts, right? And I saw residuals looking like that, right? That tells me there's a lot of residual error around the middle of the regression line. And there may be some error at the left side of the regression line, but it's in the opposite direction. I start getting this sort of spiral-looking pattern to residual error. Okay. Okay. Yeah, so there are definitely ways to diagnose. All right. So, yeah, so that's good intro into the slide. So residual is the distance a data point falls from the line that best fits the data. Now what SPSS is going to do is, in the process of doing the regression, it's going to try to fit a whole bunch of lines to the data. And the way that it decides which line is best, okay, so we would quantify residual as being the distance, say, from this point to the line, okay? Do we want to find a line that maximizes that residual or minimizes it? Minimizes it, right? So we could fit infinite number of lines through the data, but the way we're going to decide which line is the best line is to find the line that across all the possible residuals minimizes the total. Because that means, on average, the line is the closest to every other data point in the set. Does that make sense? Yeah.
How is that different from minimizing error?
How is it different from minimizing error? Well, you are minimizing error. Yeah, it's the same thing. This process should sound sort of familiar to you, though, because here we have a line, and we're calculating the deviation from that line. What does that sound a whole lot like? Yeah, it's sort of like when we were calculating standard deviations, we had to compute the deviation from the mean, right? And then we'd square that deviation, right? That would give us variance. That's essentially what we're doing here. It's the same thing, except instead of having a mean, we have a regression line, which represents a prediction of a data point. And then we take the deviation. We're essentially going to square those deviations, add up all the squared deviations. The line that has the least squared value is the best fitting line. Does that make sense? So the criterion, not surprisingly, for picking the best line, regression line, is called the least squares criterion, right? The line that results in the smallest sum of squared deviations from the line is the best line. So again, you could fit infinite number of lines, right? But they're not all going to have the same slope, right? Which means they're going to result in different squared deviations. So they're not all going to be created equal. So SPSS will find that for you. So this residual we call error. If we have a small sum of residual error, really squared residual error, but if we have a small sum of residual error, do we have a line that fits well or poorly? Yeah, it fits well. Good. And a large sum fits poorly. Good. So this is going to help us now get into regression, because we're getting to the point where what we're saying is, hey, if I have a line, say, going like this, that means I could know the value on the x-axis, right? Go up to the line and predict y. Does that make sense? Okay, so we're getting now close to regression. Okay, so the four most common correlations that we'll observe in social science literature, by far the most common one's a Pearson. Okay, Pearson correlation. So you run into Pearson before. Anytime I've said to you, hey, run a correlation on these two variables, it's been pretty much for Pearson. We use Pearson when both variables are continuous at either the interval or the ratio scale. So for continuous variables. Okay, it's not the only correlation that's out there. We can use Spearman when the data are ordinal. Okay, and so by ordinal we just mean that the data are expressed in terms of rank orders. So let's say I wanted to know the Spearman correlation coefficient between rank order finishes in the New York Marathon and the Boston Marathon. That's what I'd use, would be Spearman. I wouldn't use Pearson because rank order doesn't tell me the distance between, say, first and second place or second and third place. It just tells me who finished first, who finished second. Okay, we also use that for looking at nonlinear relationships. The third correlation you'll run into is a point by serial correlation. And that's a correlation where one of your variables is dichotomous and the other is continuous. Okay? So if I was curious whether there was a correlation between biological sex and GPA, is biological sex continuous or dichotomous?
Generally dichotomous.
Yeah, most codings would be dichotomous.
1 and 2 dichotomous.
Right. Yeah, so if we're coding males as 1, females as 2, that's a dichotomous rating. You can be in one group but not the other, and those are categories. Okay? So categorical data. GPA, though, is continuous. Right? In my day in high school, it ran from 0 to 4.0, but I guess today, what does it run to?
It depends on the school.
Yeah. So it goes over 4.0.
Yeah.
I went to my son's honors.
Like, I graduated with some stupid one because I took AP classes.
Yeah, the APs are weighted
Yeah,
differently.
I had a 4.76. It's
Yeah.
ridiculous because I took APs.
Yeah, and so many kids these days are taking AP classes that when my son graduated and gained honors, fully 1/3 of the high school had a 4.0 or higher, which I thought was amazing.
Oh,
You know, that would never have happened when I was in high school. But because all those AP classes are weighted, it
It's
happened.
because they want to give you more, like, getting an A in an AP class is a lot more difficult than getting an A in, like,
Yeah.
honors or, like, a
Sure.
regular class.
Right. So they figure there has to be some sort of reward for it, but it does mess up the calculation for sure. And then the last one is a phi coefficient. We use phi coefficients when both variables are dichotomous categorical. Okay, those are the four that you're going to most likely see. Okay,
Wait, how would you even do a correlation between two dichotomous things?
well, I'm not going to do that for you now, but basically both are categorized into two categories, right? And you can create a correlation out of that. You're just going to have to take my word for it, but the calculation is very different, obviously, from doing Pearson. Yeah, so that you can do it though. There are ways of measuring association when both variables are dichotomous, and especially when we talk about non-parametric statistics, you're going to see more of that. Yeah.
Can you give an example of another dichotomous variable other than sex?
Sure. What if you divided a sample into married versus cohabitating? Right? So just as long as there's two categories, they're mutually exclusive from one another, right? Then you have a dichotomous rating.
Treatment A versus treatment B.
Right? Yeah. As long as you can't be in both. Right? So they're dichotomous. Okay, so here's our formula, z-score formula for Pearson. And in the sample, the statistic that we'll calculate is called R. And in the population, it's rho. And the easiest way to do it is to compute z-scores for every raw score in the data set, and then compute the cross product of the z-scores. Then you sum those cross products and divide by essentially degrees of freedom, n minus 1. Okay? So, easier to show you. So let me go. This will take just a second while it pulls up Excel. Okay. Go over there. Okay. Okay, Roberto. Give me a variable that everyone in this room would have familiarity with and could provide a continuous score on.
Only thing that comes to mind is GPA.
GPA. Okay, that'll be, okay.
A little too
What?
personal.
Well, hold on, I'm thinking. Let's call it GPA of a friend you know. Okay?
Oh, okay.
All right.
Okay.
Okay, so we're going to be putting it up here.
understand.
So why don't you think of a friend you know, okay? So it's not your GPA. Okay? So write that down right now. Of a friend you know. Okay?
But if we're doing it anonymously, can we do our own GPAs?
You could, but you're not going to tell me that it's yours.
Yeah.
We're going to assume it's a friend you know.
Okay. I don't
Right.
have paper, just send me some paper. I can.
Okay.
send.
So GPA of a friend you know, this could be friend, boyfriend, girlfriend, could be you, we don't know. No one's disclosing, right? Okay? And then what I want you to give me is estimated hours studying each week.
What do you mean by studying? Like,
Engaged in assignments, studying out of class. I'll call that weekly study. Okay? That makes sense? So just say, okay, outside of class, ignore class time, because everybody has to do class time. How many hours do you think, on average, that person studies outside of class? Okay? Based on what they told you, your guesstimates, and so forth. Okay, so you should be writing these two things down. I don't want you writing these down as you're hearing data come in from everybody else. Okay? So what we're going to check to see is there a relationship between hours studied outside of class and GPA, based on your impression of somebody that you know closely. Okay, so Sally, why don't you start us up and we'll just go up and down rows.
3.86
Okay,
and 20.
okay, Alec?
4.0, 26.
Okay, now watch as I do this. You'll see for this first row, the Z is going to change with every entry. It should change, right? Because the Z score is just where this raw score ranks compared to the other raw scores on that variable. Right, Shannon?
3.7, 22.
Okay. All right, Annie?
Oh, GPA 3.74, hours 12.
Okay.
3.6
Yeah?
and 28.
Who are all these bright people you know? Doesn't anybody know, like somebody who's like on probation or anything? Come on.
no.
Ladura.
4.0 and 25.
Okay. Hey, Gabby, you're up.
3.74, 14.
Okay.
3.96, 25.
All right. Angie, how about you?
3.4, 12.
3.4 and 12. Okay.
3.5 and 25.
3.5 and 25. All right.
333 and 18.
Whoops. All right. Let's see.
3.2 and 22.
3.0 and 22?
3.2.
Oh, 3.2, okay. And 22? Okay.
3.15 and 12.
All right.
3.6 and 18.
Okay, so everybody sees what I've done, right? I've got two variables. This is our x variable, GPA. This is our y variable, weekly hours studied. Okay? Now, down here I've got the mean. So I have a mean of 3.63 for GPA with a 0.28 standard deviation. For hours studied, 19.93 with a standard deviation of 5.68. Okay? Now what I'm going to do is I'm going to take the values here, and I'm going to calculate z-scores for both every x value and every y value. Okay, everybody see how I did that? Okay, so I just basically copy and pasted, and the nice thing about Excel is it'll just, boom, puts that right in there for me. So I have the formula already calculated. There's our formula. So for this z, it's cell B4, which is right here, 3.86, minus the mean, B23, divided by standard deviation, which is B24 right here. Okay? So I get z-scores for every single one. Now what I'm going to do is multiply 0.82 by 0.01, and I'm going to get the cross product. Okay? So this rounded is 0.01. And then we're going to go down here and do that for every single one. So when we get down to this formula down here, it's going to say basically, okay, take the sum of those cross product z's, which is 5.54, divide by n minus 1. I'm going to have to change that because I've got, what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, it came out exactly right. How about that? 13. Oh, that's right, because I coded it too. Never mind. So 5.54 divided by 13, we get a correlation of 0.43. So a moderate correlation between the amount of hours studied and GPA. Okay, so positive, but certainly not as strong as a perfect correlation or anywhere close to that.
There can be factors like how difficult are the classes they're taking, like how effective the studying is.
Right. Now, what's interesting, watch what's going to happen. I'm going to change a couple of these values, and I can mess with this correlation quite a bit. So let's say I get somebody with a very high GPA, let's say 3.96, and instead of 25 hours, they say they spend 50 hours a week studying. Watch what the effect on the correlation. It's going to go up, right? Didn't go up as much as I thought it would, but it went up, 0.45. Okay, so I'll put that back to 25, drops it down to 0.43. If I take a lower correlation, or a lower GPA, 3.2, drop it down to 8, what do you think is going to happen to the correlation?
Stronger. Yeah.
Went up quite a bit.
A lot more.
Right? So, why? Because in that case, a lower value of GPA was associated with an even lower value on weekly study. That has the effect of increasing the positive correlation. Okay? All right. Okay, so what we need to do, though, as we discuss correlations, is distinguish between significance and meaningfulness. Okay? So when we say significance, what do we mean? Statistical significance, defined as what? When a correlation is statistically significant, that means that what? Same concept as when we were dealing with t-test and ANOVA. A statistically significant correlation. You know, the longer you pause on this, the more guaranteed it's going to be on the final. So, a statistically significant correlation. You guys are like, oh, now we can determine what's on the final. Now this is all we got to do is pause. Right? Okay. Means what? Yeah, so that would be indicated by p-value. But if we said that there's a statistically significant correlation between hours studied and GPA, we would be saying what?
the variations that you do? So just random error?
Yeah, you don't even really need to get into variation, but all you need to just say is that the relationship between the two variables is not likely due to chance or measurement error. That's all it means. It means the exact same thing. So when you say statistically significant correlation, you're saying, hey, I'm observing a 0.4 correlation. The likelihood that I would observe that by chance or measurement error, really small. Okay, it's the same thing as when we look at differences between means. But a significant correlation doesn't exactly mean that it's large or that it's meaningful. And here's the key, it depends on what we're studying, right? So if I say, for example, I'm interested in the relationship between a measure of a personality disorder, okay, and actual behavior, I want really high correlations, right? So let's say I design a measure for antisocial personality behavior, and then I count the number of times somebody's been arrested in their life, right? I would expect there to be a strong positive correlation with run-ins with the law, because that's what antisocial personality people do, right? They're the Dexters of the world, okay? Anthony Hopkins, Silence of the Lambs, that kind of thing. So we would expect a high correlation. And if we didn't see it, we might wonder about our measure, okay? But a 0.15 correlation might be really useful for us too if we're dealing with a new cancer drug and we're finding a small relationship between the drug and life expectancy. Okay? That might be meaningful, right? So the thing that you have to look at, how important a correlation is, you really have to look at what it is you're studying and the history of other studies in that field, right? You know, a 0.15 correlation might be an absolute breakthrough, right? It leads us in the direction of a really important effect that needs to be fleshed out a little bit more. Okay. All right. Oh, there you go. And then that leads us to the coefficient of determination and the coefficient of alienation. So this is where variance comes in. Okay. Correlation just tells us the degree of relationship between two variables and the direction of that relationship. But what if I want to know how much variance is shared by one variable or another? So imagine I have x, and x has all of its variation. And then I could draw y. Y has all of its variation. And the amount of variation that they share is called covariance. Okay, that's what they share. So it's not that x and y perfectly align. When x goes up, y goes up, or so on. But when x goes up, y goes up a little bit, right? So they share some variation. So we want to know the proportion of variability in one variable that is shared, or what we'd say, explained by another variable. That term explained by always freaks people out. What does that mean? What does it mean to be explained by? You know, how does x explain variance in y? All it means is that they share variance. Okay? X is useful in helping to explain why y changed to some degree. Okay, so explained by.
So the amount of time studying helps explain 0.4.
Yeah, the amount of time studying helps explain GPA, right? The variability in GPA. But it's only this part where they overlap, right? There's a lot of, let's imagine that x is GPA, y is our study. It's this variation that we're interested in. There's a lot of variation in GPA that has nothing to do with our study. Okay? Could be due to any of a number of other things. Yeah.
So the higher the correlation, the bigger that
Yeah. Yeah. So how do you think we're going to figure out what the explained variance is? the proportion of variance that's explained, shared between the two variables.
I have a question.
Yeah.
I know I use R squared
Uh-huh.
in other classes.
Right.
Is R squared, does that help you determine, like that's how good of a model
Yeah.
the line is, correct? Is it,
Right. Right. So, yeah, and you're talking about a slightly different R squared. You're talking about capital R squared. Okay. You're talking about lowercase for just two variables? Or I thought you were talking about regression. If you're talking about regression, I was thinking you were talking about multiple predictors on one. But yeah, it comes from that. It's the same idea. It's the same idea. Okay, so we look at, for correlation, what's called the coefficient of determination. And all it is the correlation squared. So we said that studying had a correlation with GPA of what, 0.4, what was it? 0.43. If we square 0.43, that is equal to this area right here, the overlap, the variance that those two variables share. So basically, I'll do a rough calculation in my head, but somewhere around 17%, right, 18%, something like that, of variability in GPA can be explained by hours spent studying, right? So 0.43 squared takes us to about 17%. That also means about 83% can't be explained by hours studying.
so that's the coefficient of alienation.
That's the coefficient of alienation, is what's not out there. Okay? So coefficient of alienation is just 1 minus r squared. Okay? So, keep in mind, sometimes, this is sort of a useful instruction based on your own data. Sometimes folks say, well, the amount of hours that I put in should translate into higher grade. And you know what? There is a relationship there. But it doesn't even account, based on your data, for half of the variability. Right? So, fact is, some people study more efficiently. Some people come in with strong skills. I could go on in terms of a list of things that might affect grades other than hours studied. Okay? So these are the coefficient of determination, coefficient of alienation. And by this point in psychology, you've probably had this drilled into you in this class that correlation and causation are not the same. Okay? That being said, it's hard to imagine a causal relationship that isn't at least correlational, right? I mean, that seems to be sort of a prerequisite of a causal relationship, is that it's correlational. But that does not mean that all correlations represent causal relationships. Okay, so very possible for two variables to be correlated and have no causal relationship. X could cause Y, Y could cause X. There could be a third variable. Okay. All right. And that takes us to another important point about correlation. You've got to be careful of what's called restricted range. Okay? So, with restricted range, what happens is at least one of the variables is not represented in its full range. Okay?
Like our sample.
Yeah. I mean, there's a really interesting example with GRE scores. GRE scores, on average, correlate with first-year grades about 0.20. Right? So who's interested in going to grad school? All right, a few hands. Med school, a few hands. JD, one hand. You're the one that they'll all come to for malpractice suits. So all of you are going to have to do entrance exams. And a source of debate has been, why are these correlations so low between the entrance exams and then actual performance first year of school?
So with SATs and
Yeah, and SATs aren't that much better. Okay. And, a lot of people resort to non-statistical arguments that are more design-oriented. Like it's a biased test, content validity issues, and so forth. But you can actually kind of understand this issue strictly based on restriction and range. Okay, and I'll show you how. So in other words, why do we still use the GRE? Okay, here's a frequency distribution of GRE scores. Okay, so we'll assume they're all normally distributed. And scores to the right are higher, scores to the left are lower. Okay, so everyone who wants to go to grad school takes that GRE test. All right? Who's actually going to grad school?
Oh.
Right?
People who have higher GRE scores are the ones that get accepted.
Yeah. So, makes sense, right? That if you get a high GRE score, you have a much higher likelihood of getting into grad school than if you had a low GRE score. That's just the purpose of the test. Okay? And the whole purpose of the GRE is to put everybody on sort of an even playing field, because graduate schools know that different institutions award A's or B's or whatever at different rates. So it's hard to compare directly GPAs. All right. So we have a restricted range here. And then we look at grades in grad school. Okay, let me start this out by saying, okay, you're an undergrad here at Richmond. What GPA do you have to have in order not to get into trouble? For most of you, the dean of West Hampton, right? You don't want that dean calling you, right, over GPA issues. So where does that GPA need to be to kind of stay off the dean's radar?
2.5?
It's a little lower than that. Yeah, I'm not entirely sure with Richmond. I know for Rollins, but I'm not entirely. But I would guess probably 2.0. What? 2.0. Yeah.
I just know the ones that I have to keep, so they're different.
Yeah, so 2.0, if you go below that's problematic. Okay, now for graduate school, but hey, let me back up. If you stay over 2.0, like 2.1, 2.2, you can graduate, right? Get your credits and graduate.
With grad school, don't you have to have a year?
Grad school is a little different. So when I was a faculty member at Eastern Michigan in the graduate program, the doctoral program, for clinical psych, here's our policy. If you got a B, you had a discussion with your advisor, right? Second B, you're on probation. And the third B, you're out of the program. And it wasn't any better if you got a C. That's grad school.
Just
What?
1C is already like probation, right?
Yeah, 1C is probation, 2 C's you're done. So it's a very different grading regimen, okay? The expectation in grad school is you're there to get A's. That's your job. You are there to become an expert in your field, right? And so the standards go up quite a bit.
You don't want a C student for a doctor.
That's right. Nobody would want that doctor as their doctor, right? So very different. So what happens is folks work really hard in grad school, right? It's kind of like boot camp. It's the type of thing that you don't ever want to go through again. Glad you did, but glad it's history, right? So what happens is you get a lot of A grades, a few B's, not many, and then hardly any C's, and then those folks go away, right? If you get a C in your first semester, you might be sent home, okay? So it really depends on the school, but that's fairly common. But notice what happened to this distribution. What's going on? What's going on with that distribution? What were you going to say, Gavin? You're mouthing yourself, or you're singing. I don't know. I can't tell. It's skewed, right? Are we getting the full range of grades? Yeah, not really. We're getting a whole lot more A's, right? So it's a skewed distribution. So this represents a restricted range as well. Okay? So we have a restricted range of scores trying to predict a restricted range of outcomes, which means there's not a lot of variability going on. Okay? And if there's not a lot of variability, that becomes an issue. So let me pull up this one. Okay. Now, let's imagine that we have skewed distribution of grades, where most students are getting A's. Okay. Right, and then there's, say, one student that gets a B, maybe 2, let's get one here. 2, they got to be, okay? Look at that correlation.
Oh, wow.
You see what happened?
Yeah.
I have a restricted range for GPAs so that most folks are getting A's. People get a B. Let's say this person had a really bad semester, had maybe a death in the family, ends up with a C. Right? Virtually no relationship. Okay? Now look what happens when I open it back up. So take them all back to 4s. And now let's say I get a full range in kind of in order of their aptitude. Watch what's happening to the correlation. It's not really going anywhere now because I haven't gotten down to the lowest GRE scores. Went all the way to 0.25. So it started increasing. Okay? Now, if I really start spreading out those scores, they should only increase. Yeah, it's still rounding up. We're still not getting a huge amount of range in Y. A lot more variability here. Now, if I get rid of, say, let's say everybody below 1200, say I get rid of all those folks, what do you think is going to happen to my correlation coefficient?
Not very helpful. Or will it become more helpful? Yeah.
Dropped it, right? Because again, I restricted the range, both on the scores and on the GRE and on grades. Okay. Okay, so the way we can visually represent this effect is to say, okay, we take a look at X and Y, we plot them out. There's our scatter plot. So if I were to draw a line through that scatter plot, what would it look like? Kind of went like that, something like that. Maybe it's hard to tell. Let's say it's a little flatter than that. Okay, so we might have a little bit of curvilinearity here, a little error in prediction here, but then we've also got to take into account all these scores down here. Now, if that represents a restricted range, though, and I opened up the entire range of scores, you can see what happens, right? That slope on that line absolutely changes. Does that make sense? Okay. Similarly, the effect of an extreme score on correlation can be dramatic. So if I took a look and I said, okay, here's my data set, okay? If I were to draw a line through that, probably a pretty flat line. I throw in one extreme score, right? What happens? Up it goes, right? Now all of a sudden we've got a positive correlation. Okay, we'll skip that one. So big picture. Correlation tells us the degree of linear association. But it really doesn't help us with curvilinear. It's a measure of association, not causation. The sign tells us direction, the number tells us magnitude. The restricted range of scores on either variable reduces the size of the correlation. So you got to be careful of that. It's also the foundation for regression. And the big difference between regression and correlation is that correlation does not help us predict the value of X if we know the value of Y and vice versa. Okay? Okay. Now hold on, I got one last thing to show you, then we'll be done for the day. Let's see. Okay, I want to show you this, and then we're going to talk about this on Thursday.
21 seconds. Solid rocket booster engine gimbal now underway. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Roger, roll, Challenger. Good roll program confirmed. Challenger now heading down range. Engine's beginning throttling down now at 94%. Normal throttles for most of the flight, 104%. We'll throttle down to 65% shortly. Engines at 65%. 3 engines running normally. 3 good fuel cells. 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3 nautical miles.
So the 25th Space Shuttle mission is now on the way after more delays than NASA cares to count. This morning it looked as though they were not going to be able to get off.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
Looks like a couple of the solid rocket boosters blew away from the side of the shuttle in an explosion.
Flight controllers here looking very carefully at the situation. Obviously a major malfunction. We have no downlink.
Is that focusing on the shuttle itself?
We're awaiting
No,
word
they
there.
didn't know. It was just the. Well, these are fragments of the shuttle, yeah,
Sure
but they
as
didn't know where
everyone else
the
is.
cockpit
We
was.
saw it
right?
just a few moments ago,
Yeah.
about 45 seconds after liftoff, a huge fireball in the sky.
We have a report from the flight dynamics officer that the vehicle has exploded. Flight director confirms that. We are looking at checking with the recovery forces to see what can be done at this point. Contingency procedures are in effect. We will report more as we have information available. Again, to repeat, we have a report relayed through the flight dynamics officer that the vehicle has exploded. We are now looking at all the contingency operations and awaiting word from any recovery forces in the downrange field.
What appears to be a major catastrophe in America's space program. Challenger, only seconds after leaving the launch pad, according to NASA, has exploded in midair. No word yet on if there are any survivors.
So, how many of you have seen that video? Anybody? A couple of, okay. Yeah, so it's interesting because when I showed it last semester, I was sort of thinking that everybody's seen it, but actually, no. Yeah, most people haven't seen it. This is 1986. I was very much like you. I was a senior in college, finishing up at UC San Diego, taking classes. Had turned on the radio that morning and heard the Challenger had exploded. Hadn't seen the video. Went to class. Teacher announced that it had happened. It was the biggest event of the year. So really, really sad. I mean, it was, a very different time, back then too. Right now we have a space program that's been sort of farmed out to private interest. Back then the space program was, everyone would kind of wait to see where the launches were and how it was going. And even though it may not be something you might not watch it, but you'd hear about it, you'd be interested in those launches. So in this particular catastrophe, it was especially bad because NASA had a competition for a teacher to go into space. So Chris McAuliffe won that competition, and she was on board, and she was going to beam back lessons to students around the country from space. So kids around the country were watching when that happened. So it had a real effect on society. Now, why am I showing it to you in here? Because there's a reason why Challenger blew up, obviously, and it has to do with the O-rings. And so on the solid rocket boosters, the sections of the boosters are sort of connected with rubber O-rings, and those O-rings are meant to flex so that as the fuel heats up and expands, the O-rings expand. They keep a seal right around the booster. What they found was this was an unusually cold Florida morning. So when they lifted off, the rubber didn't flex. That created a gap as the metal expanded in the booster between the seal and the metal, which allowed fuel to escape that was ignited, and you got an uncontrolled burn of all the hydrogen at one time. So what you got was an explosion rather than a controlled burn of the hydrogen. So when we come back on Thursday, I actually have a data set that we're going to go through that shows how if they had appreciated restriction of range, which we talked about today, if they had fully appreciated the ramifications of restricted range, they could have predicted that a problem was going to occur. And to be fair, the engineers did. The engineers were telling the NASA leadership that they were risking to not fly. In fact, there were lots of calls the night before. NASA leadership decided ultimately to go, and this was the result. But we actually had the data that they were looking at. So we'll use that to show regression, okay?
Yeah, I know there's one guy in particular who was the one doing these calculations.
Yeah.
He told them explicitly, if you do this, everyone will
Right.
die. Like,
Yeah.
he actually said that to them, and they went ahead with it anyway. They
Yeah.
listened to him.
Yeah, it was a.
And he apparently suffered like severe depression for the rest of his
I'm
life.
sure.
And just
That would be hard to bear. So I'll see you guys on Thursday, okay?